first question asks us to complete a table by drawing the graph, explaining the relationship between variables, and solving the given practice problem. So the first gas law is Boyle's law, which shows an inverse relationship between pressure and volume. So when the volume is low, we expect the pressure to be high. This is because as volume decreases, collisions between gas particles become more likely, so pressure increases. For the practice problem, a sample of gas has a volume of 5.6 liters at a pressure of 1.5 atm. If the gas is compressed to 4.8 liters, what's the new pressure going to be? So the volume is decreasing here, which means we expect the pressure to increase. So we're expecting an answer that's bigger than 1.5 atm. So I'm going to use P1V1 equals P2V2, which is Boyle's law. We're going to go ahead and plug in all of the numbers that we know, and we're solving for P2. So I get 1.75 atm, which whenever we round for sig figs, we need 2. We get 1.8 atm. The next gas law is Charles's law. So this is the direct relationship between temperature and volume. So as volume increases, temperature increases. This is because pressure is being held constant. Normally, if you increase temperature, we would expect pressure to go up. But because pressure is held constant, the volume increases instead. So increasing the volume decreases pressure, so that counteracts the rise in pressure that we would get from raising the temperature. So a volume of gas is 2 liters at 200 Kelvin and constant pressure. What must the Kelvin temperature be for the volume of the gas to be 4 liters? So we're doubling volume, and since this is a direct relationship, we expect to double temperature. So we're going to use Charles's law, V1 over T1 equals V2 over T2. We're solving for T2, which is in the denominator, so the best way to handle that would just be to cross multiply. And then go ahead and divide by 2 liters to solve for T2. So I get 400 Kelvin, which is what we expected. The next gas law is Gay-Lussac's law. This is the direct relationship between temperature and pressure. So as temperature rises, pressure rises. This is because as you increase the temperature of a gas, its particles have more kinetic energy, meaning that they move faster. So collisions become more likely, which means the pressure goes up. A sample of gas is held at constant volume. If the temperature is doubled, what will happen to the pressure? So since this is a direct relationship, if temperature doubles, then pressure should also double. The next question is an ideal gas law problem. So we have a 7.50 liter sealed jar at 18 degrees Celsius with 0.125 moles each of oxygen and nitrogen. What is the pressure in the container? So we're going to use PV equals nRT, and we're solving for P. So whenever I plug in my numbers, I'm going to choose the first R constant here just because I decided I want my answer to be in kilopascals. The problem didn't specify what pressures we wanted. So whenever you choose an R value, you just got to pick the one that matches your units. They all have liters, moles, and Kelvin, but they have different units for pressure. So I solve for the pressure in kilopascals. Whenever I round that for sig figs, I get 80.6 kilopascals. And here are the answers if you chose a different unit of pressure to get your answer in. Number 3, a 500 milliliter metal cylinder is holding 0.1 moles of helium gas. It's known to rupture at a pressure of 10 atmospheres. So at what temperature in degrees Celsius is this container going to break? So first I converted my 500 milliliters into liters. And since we're solving for T, I'm going to use PV equals nRT. I'm going to divide both sides by N times R, so I get T. And then I can go ahead and fill in numbers. I chose for my R constant the one that has ATM because pressure is given in ATM. So whenever I plug this in and solve, I get 609 Kelvin. But the question asks for it in Celsius, so I'm going to subtract 273.15, and I get 335.86 degrees Celsius. We need to have only one sig fig here, so this rounds to 300 degrees Celsius. For question 4, a balloon is filled at 298 Kelvin at 1 atmosphere to a volume of 2 liters. If you let go of that balloon and it rises up into the atmosphere, it will rise up until it's equally buoyant to the atmosphere, where the temperature in this case is 263 Kelvin and the pressure is 0.667 atm. What is the new volume? So this is a combined gas law problem. So we're going to use P1 V1 over T1 equals P2 V2 over T2. And we're solving for V2 in this case. So the best way to handle that, we're just going to cross multiply here and then divide so I can get V2. We notice that all the units cancel except for liters. So then when we round this for sig figs, V1 has only one sig fig, so V2 can only have one sig fig. So we get 3 liters when we round. Question 5 is about Avogadro's law. So the flasks below each contain a sample of gas. They're at the same pressure and temperature, but which one has more moles of gas? So flask 2 has a larger volume than flask 1. And Avogadro's law says that for 2 gases at the same pressure and temperature, a greater volume indicates that there's more moles of gas present. So flask 2 has more moles than flask 1. Number 6 is a partial pressure question. And a big hint to that is that we have a mixture of 2 different gases. So Dalton's law of partial pressures says that the total pressure exerted by a gas is equal to the pressure exerted by the sum of each gas in the mixture. So basically the total pressure is the sum of the partial pressures. So we've got oxygen and some other gas, and that would give us the total pressure. We know the pressure of oxygen is 80 millimeters of mercury. We don't know the pressure of the other gas, but we do know the total pressure. So here we're just solving for the partial pressure of the other gas. We get 40 millimeters of mercury. Question 7 is an effusion question. So order the gases from slowest to fastest rate of effusion. So effusion is the movement of gas particles through a small hole in their container. And this occurs just due to the random motion of gas particles. Graham's law says that the rate at which a gas effuses is inversely proportional to the square root of their molar masses. So what that means is that heavier molar masses are going to be slower moving. So here I found the molar mass of each of those gases, methane, ethane, and propane. So methane is going to be the fastest and the propane is going to be the slowest, and this ranking is just based on their molar mass. Question 8 is about some manometers. So in the picture, which gas is exerting a greater pressure? Is it the carbon dioxide that's in the bulb, or is it the atmosphere? So based on the picture, the carbon dioxide has to be exerting a greater pressure because the mercury in the manometer has been displaced towards the atmosphere, away from the carbon dioxide. So then question B says, okay, well, what is the pressure being exerted by the atmosphere? So first things first, we've got a bunch of different units here. So I'm going to go ahead and convert the 1.51 atm into millimeters of mercury. So now I know that the pressure of the carbon dioxide is 1,147.6 millimeters of mercury. Well, I know that it's pushing 324 millimeters of mercury harder than the atmosphere. So I need to subtract out the difference in pressure. So this means that the pressure of the atmosphere is 823.6 millimeters of mercury. So the pressure of the carbon dioxide, we have to subtract out because the carbon dioxide is pushing harder than the atmosphere to get the pressure of the atmosphere. And if you notice in the picture, it says XKPa, meaning that we want the pressure in kilopascals. So I'm just going to go ahead and convert the 823.6 millimeters of mercury into kilopascals.